Newton's understanding of gravity was good enough for us to fly from Earth to the moon. Still, it's fun to think that we could achieve such feats using something that is ultimately only an approximation. Everything in our universe seems to be perfect, regulated by laws, but despite decades of research, certain mysteries remain unsolved. Questions such as why time moves in one direction, the nature of reality, the existence of gravity, and why time slows down when we travel at the speed of light have fascinated us for millennia. What if I said that gravity is a lie, but a construct of the human brain? It may sound unbelievable, but that is exactly what the famous physicist Brian Cox recently claimed. To understand the nature of gravity and why time slows down, we must go beyond Newton. The problem with Newton's theory of gravity is not what he understood, but what he didn't address. Newton's theory allows us to predict how things move under the influence of gravity, but it does not explain why gravity exists or how it works. Newton knew this and basically attributed it to God, implying that the system of the sun, planets, and comets could only continue to function under the control and advice of an intelligent being. The vast universe around us has mysteries waiting to be revealed, especially the enigmatic phenomena of time and gravity, two fundamental properties of our existence. Imagine a world where time behaves strangely, where it can slow down or speed up, and where the force that keeps us on Earth may not be what it seems. This is the realm of Albert Einstein's theories of relativity, which gives a strange twist to our understanding of time and gravity. Albert Einstein, a name known to many, offered a new perspective on the universe through his theories of relativity, which laid the foundation for our understanding of how time behaves under different conditions, especially at extreme speeds. At the beginning of the 20th century, Einstein proposed two amazing theories: special relativity and general relativity. The special theory of relativity, published in 1905, changed our understanding of time and space. This tells us that the laws of physics remain the same for all non-accelerating observers, regardless of their motion. This theory introduces the concept of relativistic effects, including the idea that time can expand or slow down under certain conditions. One interesting thought experiment used to explain time dilation is the light clock. Imagine that you are inside a spaceship traveling at an incredible speed, close to the speed of light. Inside the spacecraft is a beam of light that bounces between two mirrors perpendicular to the direction of travel. To an observer inside the spacecraft, the light appears to travel in a straight line in the vertical direction of the bounces. But to an outside observer not moving with the spacecraft, the light beam has to travel a greater distance to hit the mirror because of the high speed of the spacecraft, so the light appears to take a longer diagonal. Since the speed of light is constant for all observers, the time required for the light beam to travel should be the same both inside and outside the spacecraft. But since the path is longer for an outside observer, it seems that the light would need more time to complete the journey. Einstein called this apparent time difference between two observers time dilation. Time slows down for a moving observer relative to a stationary observer. This concept is not just theoretical. Experiments have confirmed these relativistic effects. For example, particles from particle accelerators, such as the Large Hadron Collider, can reach close to the speed of light. Scientists must consider the effects of time dilation in order to make accurate predictions and measurements. Special relativity opens the door to a world where time is not constant, where it can be stretched and compressed depending on motion. It challenges our everyday intuition and makes us realize that the universe works in ways that transcend our common experience. Einstein's special relativity shaped our understanding of the structure of the universe, especially in relation to time and motion. One of the main ideas of this theory is that the speed of light is the same for everyone, regardless of where they are moving. This is contrary to our everyday experience, where speeds tend to increase as we move. The universe seems to have a built-in speed limit, the speed of light. In special relativity, simultaneous events may not be simultaneous for everyone. If two events happen in different places and you move relative to those events, what you see happening at the same time may not be simultaneous to someone else from a different perspective. This seemingly strange idea challenges our traditional understanding of time. The concept of time dilation is one of the most interesting and practical implications of the theory. The faster you move, the slower time appears to you relative to a moving observer. This effect becomes stronger as you approach the speed of light. Imagine two identical twins, one on Earth and the other traveling through space at a significant fraction of the speed of light. When the spacefaring twin returns, they are younger than their Earth sibling. This phenomenon, often called the double paradox, is a real consequence of time dilation. The reason for this strange behavior is the immutability of the speed of light. As the spacefaring twins accelerate to high speeds, their clock is ticking. However, to an observer on Earth, the clock of a twin clock moving in space appears to slow down as the twin moves relative to Earth. Another consequence of special relativity is long contraction. When an object is moving at high speed, its length appears shorter to an observer standing in the direction of movement. This effect is small at everyday speeds, but becomes more noticeable as the object approaches the speed of light. One of the most famous equations in physics, E equals mc squared, is a direct result of special relativity.
This equation states that energy and mass are interchangeable, meaning that mass can be converted to energy and vice versa. This principle is important for understanding the behavior of particles at high speeds and the energy released in processes such as nuclear reactions. Special relativity is not just a theoretical concept, it has real-world applications. For example, GPS systems depend on the precise timing of satellite signals. Since these satellites are moving relative to us, the time dilation effect comes into play. If the effects of special relativity were not taken into account in GPS calculations, our navigation systems would be significantly less accurate. Special relativity forces us to rethink our intuitive notions of time and space. It shows that the universe works in ways that defy everyday experience. Time is not an absolute concept, but relative, due to movement. The constancy of the speed of light and the ratio of energy to mass are central ideas that have been confirmed by many experiments. We now turn to general relativity, another pioneering concept introduced by Albert Einstein in 1915. This theory takes us into the world of gravity and reveals a deep connection between gravity and the structure of the universe. Basically, general relativity challenges the classical understanding of gravity as a force acting at a distance between masses. Instead, it represents gravity as a consequence of the curvature of spacetime. To understand general relativity, think of the universe as a four-dimensional entity that combines 3 dimensions of space and 1 dimension of time. In this four-dimensional spacetime, massive objects like stars, planets, and even you cause spacetime to curve around them. We see this curvature as gravity. Imagine spacetime as a huge elastic fabric. A massive object, such as the soil, creates a hole in this fabric. If you place a smaller object near the ground, such as a ball, it will roll toward the well. This is analogous to what happens when an object falls under the influence of gravity. It is not a mystical power. It just follows the curvature of spacetime. General relativity provides a powerful explanation for the movement of celestial bodies in our solar system. It correctly predicts planetary orbits, such as the elliptical path Earth follows around the Sun. The old idea of gravity as an attractive force did not fully explain these orbital motions, but the concept of curved spacetime did point. One of the most striking confirmations of general relativity came during the solar eclipse of 1919, when Sir Arthur Eddington led an expedition to observe the bending of starlight by the sun's gravity. According to the theory, the massive presence of the sun would bend the light path of distant stars, causing them to shift slightly from their normal position. Eddington's observations matched Einstein's predictions, providing strong evidence for the curvature of spacetime. Another intriguing prediction of general relativity is the existence of black holes, regions of spacetime where gravity is so strong that nothing, not even light, can escape. The idea of black holes naturally comes from the mathematics of general relativity. When a massive star undergoes gravitational collapse, it can create a singularity, a point of infinite density surrounded by an event horizon beyond which nothing can return. In recent years, we have obtained direct evidence of black holes through observations of gravitational waves. These are ripples in spacetime caused by the acceleration of massive objects. When two black holes merge, they create gravitational waves that travel through the universe. The detection of these waves by observatories such as LIGO, Laser Interferometer Gravitational Wave Observatory, confirmed the existence of black holes and provided further support for the theory of general relativity. One of the most memorable aspects of general relativity is the idea of dilation near massive objects. Just as time slows down when we move at high speeds, it also slows down in strong gravitational fields. This means that time passes more slowly for an observer close to a massive object than for an observer further away. This effect, known as gravitational time dilation, has been observed and measured. For example, precise atomic clocks placed at different altitudes show that time passes slightly faster at higher altitudes, where gravity is weaker.